A baby planet is forming around a young star, and it looks like our solar system's birth. You know what's ironic? Astronomers spend billions building telescopes to take baby pictures, not just any baby pictures, mind you, but photographs of planets being born around distant stars. It's basically the universe's version of posting ultrasound photos on social media, except instead of "look at little Timmy's first heartbeat," it's "check out this protoplanet accreting gas at 6 billion tons per second." The engagement is about the same though, mostly scientists double-tapping and leaving comments like, "beautiful structures in that accretion disk." But here's the thing, these cosmic baby pictures just revealed something that changes everything we thought we knew about how worlds come into existence. In the summer of 2025, astronomers made a discovery that sent shockwaves through the scientific community. They didn't just find evidence of planets forming around distant stars. They caught the exact moment when cosmic dust begins transforming into the building blocks of worlds. What they witnessed looks remarkably similar to what our own solar system must have experienced 4.6 billion years ago. We're seeing our own birth story playing out in real time, 1,300 light-years away. Two telescopes pointed at the same infant star and captured something never seen before. The star is called HOPS 315. It sits in the constellation Orion, embedded in a thick cloud of gas and dust. At just 100,000 years old, this star is practically a newborn. Our Sun is 4.6 billion years old. If the Sun were a 46-year-old adult, HOPS 315 would be roughly 16 hours old. We're seeing a stellar infant still in its cosmic crib, not yet emerged from the gaseous envelope that birthed it. The location in Orion is significant. This constellation hosts one of the most active star-forming regions in our galactic neighborhood. The Orion molecular cloud complex spans hundreds of light-years and contains enough material to create thousands of stars. Young stars pepper the region, each surrounded by its own disk of gas and dust. It's a stellar maternity ward, with births happening constantly across this vast cosmic nursery. HOPS 315 is just one infant among many, but it happens to be oriented perfectly for our observations. We're viewing its disk nearly edge-on, which allows us to see structure and chemistry that would be hidden if we were looking at the disk face-on. Dr. Melissa McClure from Leiden University led the international team that made the discovery. McClure has spent her career studying the chemistry of protoplanetary disks, trying to understand how simple molecules transform into the complex ingredients needed for planets and potentially life. She knew that observing HOPS 315 would be challenging. The star is deeply embedded in its natal cloud, surrounded by thick layers of dust that absorb visible light. Traditional optical telescopes see nothing but darkness in that direction. The dust completely obscures the star and its disk. That's where infrared astronomy becomes crucial. Dust particles absorb short wavelength light like visible and ultraviolet, but they allow longer wavelengths like infrared to pass through relatively unimpeded. It's similar to how fog blocks your vision during the day, but infrared cameras can see through it. By observing at infrared wavelengths, astronomers can peer inside dusty regions and see what's happening at the cores of star-forming clouds. McClure's team combined observations from two of the most powerful instruments humanity has ever built: the James Webb Space Telescope in orbit, positioned at a gravitationally stable point 1 million miles from Earth, and the Atacama Large Millimeter Array in Chile's high desert, at an altitude of 16,500 feet, where the thin, dry air provides exceptional observing conditions. These aren't just telescopes, they're marvels of engineering. Webb's primary mirror measures 6.5 meters across and consists of 18 hexagonal segments coated in gold to maximize infrared reflection. ALMA comprises 66 radio dishes that work together as a single giant instrument, synthesizing a telescope effectively hundreds of meters across. Together, these instruments peer through the dust clouds that normally hide young stars from view. Webb observes at near and mid-infrared wavelengths, detecting warm molecules and dust. ALMA observes at millimeter wavelengths, mapping cooler gas and tracking molecular motion through Doppler shifts. Each telescope sees complementary information. Webb reveals the hot inner disk where temperatures reach thousands of degrees. ALMA maps the cooler outer regions and traces the overall disk structure. By combining data from both instruments, astronomers create a complete picture from the inside out. What they found shocked everyone. For the first time in history, astronomers detected silicon monoxide molecules in the process of condensing from hot gas into solid mineral grains. Not just silicon monoxide gas, which had been seen before in protoplanetary disks, and not just solid silicate minerals, which exist in meteorites and interplanetary dust, but both simultaneously. Gas in the process of transforming into solid, the phase transition captured as it happens. This is time zero for planet formation, the instant when worlds begin. The data showed characteristic spectral features from both gaseous and solid-state silicon monoxide. Molecules in the gas phase vibrate and rotate, emitting light at specific wavelengths determined by quantum mechanics. These emission lines are sharp and distinct. Solid crystals, by contrast, have their atoms locked into rigid lattices. The vibrations are different, producing broader absorption features at slightly different wavelengths. The Webb data contained both signatures, indicating that silicon monoxide exists in multiple forms simultaneously around HOPS 315. Moreover, the team could determine where these different forms exist. The gaseous silicon monoxide appears in narrow jets, streaming away from the star at high velocities, measured by ALMA through Doppler shifts. These jets are common around young stars. They're powered by magnetic fields that channel material from the inner disk and launch it into space at speeds exceeding 10 kilometers per second. But here's the crucial observation. The jets contain less silicon monoxide than expected based on the disk's composition. Some of the silicon is missing from the gas phase. Where did it go? It condensed into solids that remain in the disk, rather than being carried away in the jets. The solid-state silicon monoxide signature detected by Webb comes from a small region close to the star, within a few astronomical units. This region is hot enough for silicate minerals to glow in infrared light, but cool enough for gas to condense into solids. It's the Goldilocks zone for mineral formation. Not too hot, not too cold. Just right for silicon monoxide to transition from gas to crystalline silicate grains. And that's exactly what's happening right now around HOPS 315. Think of it like watching flour, water and yeast combine to make bread dough. Before this moment, you only had separate ingredients. After this moment, you have something that will eventually become bread. But the analogy goes deeper. In baking, you can't just mix the ingredients at any temperature. Too cold and nothing happens. Too hot and you kill the yeast. There's a specific temperature range where the magic occurs. Same with planet formation. Silicon monoxide only condenses when conditions are precisely right. Temperature, pressure, and chemical environment must all fall within specific ranges. McClure's team caught the universe's kitchen in action. They witnessed the exact moment when formless gas starts becoming solid matter. The matter that will eventually clump together, grow larger, accumulate into boulders, then mountains, then planetesimals, then planets. But let's understand this process in more detail, because it's remarkably complex and depends on subtle physics that we're only now beginning to observe directly. When a star forms, it creates heat through gravitational contraction. Material falling onto the growing star releases potential energy, heating the surrounding disk. The temperature profile in the disk follows a gradient, hottest near the star, where material is densely packed and rapidly accreting. Cooler further out, where the disk is more diffuse and receives less direct heating. This temperature gradient creates different chemical zones, each with its own characteristic minerals. Very close to the star, temperatures exceed 2000 degrees Fahrenheit. At these temperatures, even the most refractory materials remain gaseous. Nothing condenses. Everything stays in vapor form. But as you move outward and temperatures drop, different materials begin to condense in a predictable sequence. Silicon monoxide condenses first, at around 2200 degrees. Then other silicates at slightly lower temperatures. Iron and nickel condense around 1800 degrees. Troilite, an iron sulfide mineral, condenses at about 1300 degrees. Each mineral has its own condensation temperature, creating a layered structure in the disk, like the rings of a tree.
This condensation sequence explains the composition of planets in our solar system. Mercury, closest to the Sun, formed in the hottest part of the disk. It's unusually metal-rich for its size, with an oversized iron core making up about 85% of its radius. Venus and Earth formed slightly further out, where silicate minerals were more abundant relative to metals. Mars formed even further out in a region that was cooling down and had less total material available, which explains why it's smaller than Earth. The asteroid belt represents the transition zone between rocky and icy materials, and the gas giants formed beyond the frost line where water ice dramatically increased the available solid material. Here's why this matters. Every rocky planet in our solar system started this way. Earth began as silicon-rich minerals condensing in a hot disk around the young sun. Those first solid particles stuck together through static electricity. When dust particles collide gently, their surfaces have slight electrical charges that cause them to cling together. It's the same principle that makes a balloon stick to your hair after you rub it on your head. In the protoplanetary disk, countless collisions happen every second. Most particles bounce off each other, but some stick, and once two particles stick together, they form a slightly larger particle that can stick to others. Gradually, they grow. Dust became pebbles, pebbles became rocks, rocks became boulders, boulders became asteroids, asteroids collided and merged into planet-sized objects. The process took millions of years, but it all started with that first condensation, gas becoming solid. But there's a problem. A major problem that puzzled planetary scientists for decades. It's called the meter-size barrier. Once particles grow to about a meter in diameter, they start experiencing significant drag from the surrounding gas. The gas in the disk orbits slightly slower than the particles because it's partially supported by pressure gradients. The particles, feeling the drag, lose angular momentum and spiral inward toward the star. Calculations show they should spiral inward on timescales of just a few hundred orbits, far too fast for them to grow into planets. A meter-sized boulder orbiting at Earth's distance would crash into the Sun within 1,000 years, nowhere near enough time to accumulate into a planet. For years, this was a fundamental mystery. How did particles get past the meter-size barrier? How did they survive long enough to grow into planetesimals? The answer involves several mechanisms working together. One is called the streaming instability. In regions where particles are concentrated, they can interact with the gas in complex ways that cause them to clump even more. If the concentration gets high enough, the clump can collapse under its own gravity, bypassing the meter-sized barrier entirely by jumping straight from centimeter-sized pebbles to kilometer-sized planetesimals. It's like particles deciding to skip adolescence and jump straight to adulthood. Another mechanism involves pressure bumps in the disk. The disk isn't perfectly smooth. Variations in density and temperature create pressure maxima, where particles can accumulate without spiraling inward. These become safe havens where particles collect and grow efficiently. Think of them like eddies in a stream where leaves collect. The particles gather in these special zones, protected from the drag that would otherwise doom them. Recent observations, including studies of disks like WISPIT 2, reveal that these pressure bumps are common and often associated with planetary gaps. When a planet begins clearing a gap, it creates pressure maxima at the gap edges, where material piles up. These become ideal locations for additional planet formation. One planet seeds the formation of others nearby. This might explain why we see multi-planet systems so commonly. Planets don't form in isolation. They form in batches, each influencing the other's formation and evolution. Until now, we could only study this process indirectly. Ancient meteorites contain minerals that formed 4.6 billion years ago during our solar system's birth. Scientists analyze these space rocks in laboratories. They measure isotope ratios. They determine formation temperatures. They reconstruct what conditions must have been like. It's like doing archaeology, except your artifacts are older than Earth itself. These meteorites told us that the first solids formed at temperatures above 2,200 degrees Fahrenheit. They told us which minerals condensed first. They gave us clues about timing and location. But meteorites are fossils. They preserve ancient evidence, but they're static, frozen in time. You can't watch the process happening. You can only see the end result and work backwards. That changed in July 2025. McClure's team published their findings in the journal Nature. The paper showed direct,
real-time observations of minerals condensing around HOPS 315. Not fossils, not indirect evidence. Active, ongoing planet formation, captured as it happens. The observations reveal silicon monoxide gas surrounding the infant star. But here's the key detail. Some of that gas has already solidified into tiny crystalline minerals. The team can tell because different forms of silicon monoxide emit light at different wavelengths. Gaseous molecules have one signature, solid crystals have another. The data shows both signatures simultaneously. This means condensation is actively occurring right now. Some gas has already frozen into solids, while more gas continues to condense. Dr. Edwin Bergen from the University of Michigan, a co-author on the study, explained what they're seeing. This process has never been observed before in a protoplanetary disk, or anywhere outside our solar system. We're watching the birth of the seeds of planets, the very first solid material that will eventually become worlds. The location matters too. The condensing minerals sit roughly 2 to 4 astronomical units from HOPS 315. 1 astronomical unit equals the distance from Earth to the Sun, so we're talking about the same region where Earth and the asteroid belt orbit our Sun. The parallel is striking. In our solar system, the first minerals condensed at similar distances from the young Sun. Those minerals eventually became the building blocks of Mercury, Venus, Earth, and Mars. Now we're seeing the same process at the same location in another stellar system. Dr. Merrill Van Toff from Purdue University captured the significance perfectly. We're seeing a system that looks like what our solar system looked like when it was just beginning to form. It's a picture of the baby solar system. The conditions match, the location matches, the chemistry matches. We're looking at our own origin story. But HOPS 315 isn't the only cosmic nursery revealing its secrets. Just weeks after that announcement, another team made a complementary discovery. They found an actual planet, not just the ingredients for planets, but a fully formed gas giant sitting in a gap it carved through its parent star's disk. The planet is called Wispit 2b. Its discovery confirms theoretical predictions that had never been directly observed until now. For decades, astronomers noticed something strange about protoplanetary disks. These swirling disks of gas and dust around young stars often show rings and gaps. Like vinyl records, like tree rings, concentric circles of material separated by dark spaces. The gaps puzzled scientists initially. Why would disks have empty zones? What clears out the material? Computer simulations suggested an answer: forming planets. A planet growing in the disk would gravitationally attract nearby material. Some falls onto the planet, making it larger. Other material gets scattered away, pushed either inward toward the star or outward away from it. The result is a cleared gap centered on the planet's orbit. This made theoretical sense. The math worked perfectly. Simulations showed it happening, but observations never confirmed it. Astronomers saw plenty of disks with gaps. They even suspected planets might be hiding in those gaps, but they couldn't prove it. The planets were too faint to detect, the disks too bright and obscuring. Evidence remained circumstantial, until August 2025. Rochelle Van Kapeleveen was a PhD student at Leiden University when she made the discovery. Her team used the European Southern Observatory's Very Large Telescope, combined with the Magellan Telescope's Adaptive Optics system. They observed a star called WISPIT-2 in the constellation Aquila. The star is about 5 million years old, young, but not as young as HOPS 315. Infrared images revealed a beautiful multi-ringed disk surrounding WISPIT-2, at least 3 distinct rings separated by dark gaps. Van Kapeleveen's team focused on one particular gap. They used extreme contrast imaging techniques to suppress the star's glare and search for faint objects nearby. And there it was, a small point of light embedded directly in the gap. Follow-up observations confirmed it wasn't a background star. It was moving with Wispit 2, orbiting the star. They had found a planet, a baby planet approximately 5 times Jupiter's mass, still growing,
still accumulating gas and dust from its surroundings. Discovering this planet was an amazing experience, Van Capelleveen said. We were incredibly lucky. Wispit 2 is located in a little studded group of young stars, and we did not expect to find such a spectacular system. This system will likely be a benchmark for years to come. The significance cannot be overstated. This is the first confirmed detection of a planet sitting in a gap in its protoplanetary disk, the smoking gun linking gaps to planets. Theorists have been predicting this for 30 years. Now we have proof. Planets do clear gaps. Wispit 2b is doing exactly what the simulations said it should. It's secreting material from within its gap, while gravitationally scattering other material away. The process sculpts the disk structure, creating the rings we observe. Dr. Christian Ginsky from the University of Galway, a senior researcher on the project, described what's happening. One might almost think of the planet like a vacuum cleaner, sucking up all the dust. It clears out a gap as it orbits because material falls down onto the planet. This analogy works perfectly. The planet isn't pushing material away mechanically, it's gravitationally attracting nearby gas and dust, consuming some while deflecting the rest. Wispit 2b is still forming. It's not done growing. The planet glows in infrared light, radiating heat from the material falling onto it. This accretion process is violent and energetic. Gas spirals down onto the planet at supersonic speeds, creating shock waves that heat the material to thousands of degrees. As it cools, the gas releases energy as light. Astronomers can measure this emission and calculate how fast the planet is growing. Current estimates suggest Wispit 2b accumulates about 1/10,000,000th of Jupiter's mass per year. That might sound tiny, but over hundreds of thousands of years it adds up significantly. The multi-ringed structure of Wispit 2's disk hints at additional planets. Each gap might harbour another world. The inner rings could indicate a smaller, rocky planet forming closer to the star. The outer rings might mark the location of another gas giant further out. Future observations will search for these hidden siblings. If multiple planets exist, Wispit 2 could be developing an entire planetary system similar to our own. Small rocky worlds inside, gas giants outside, separated by gaps and rings. Meanwhile, in October 2025, astronomers studying a rogue planet witnessed something never seen before, a cosmic growth spurt. The object in question is called CHAR 1107-7626. It's been known since 2008. Located in the Chameleon constellation, this world masses between 5 and 10 Jupiters. But here's what makes it strange. CHAR 1107-7626 doesn't orbit a star. It's wandering through space alone, a planetary mass object without a parent star. Astronomers call these rogue planets. They're surprisingly common. The Milky Way might contain billions of them, ejected from their home systems through gravitational interactions, or forming independently from collapsing gas clouds. What makes CHAR 1107-7626 particularly interesting is that it has its own disk, like a star. Young stars are surrounded by accretion disks of gas and dust that feed their growth. Chapter 1107-7626 has a similar structure despite being a planet mass object. This suggests it might have formed more like a star than a traditional planet. Instead of building up gradually in a protoplanetary disk, it might have formed from a collapsing cloud of gas, a failed star, or a sub-brown dwarf. The terminology gets fuzzy at these boundary cases. In fall 2025, observations from the Very Large Telescope and James Webb Space Telescope revealed something extraordinary. Chapter 1107-7626 was in the middle of a feeding frenzy. The planet was accumulating material from its disk at an astonishing rate, about 6 billion tons per second. That's 8 times faster than measurements taken just months earlier, the strongest growth rate ever recorded for any planet of any kind. Dr. Ray Jayawardhana from Johns Hopkins University, a senior author on the study, described what they witnessed. "We've caught this newborn rogue planet in the act of gobbling up stuff at a furious pace. Monitoring its behavior over the past few months, with two of the most powerful telescopes on the ground and in space, we have captured a rare glimpse into the baby phase of isolated objects not much heftier than Jupiter. Their infancy appears to be much more tumultuous than we had realized. This growth spurt wasn't an isolated event. Archival data revealed that CHAR 1107-7626 experienced a similar burst in 2016. This suggests episodic accretion. The planet grows steadily for a while, then suddenly accelerates its growth rate before settling back down. What triggers these bursts remains unclear. Instabilities in the disk might cause material to suddenly dump onto the planet. Changes in the magnetic field could channel gas more efficiently. Or perhaps the disk accumulates material gradually until it reaches a critical threshold, then collapses inward all at once. The discovery challenges conventional thinking about planet formation. Traditionally, planets form in disks around stars. The star provides the gravitational anchor and much of the heat that drives disk dynamics. But CHAR 1107-7626 formed without a star, or at least, it doesn't have one now, yet it's exhibiting star-like behavior, growing episodically, maintaining a disk, generating magnetic fields strong enough to channel accretion. The boundary between planets and stars is blurrier than we thought. Dr. Alex Schultz from the University of St. Andrews noted the implications. "We're struck by quite how much the infancy of free-floating planetary mass objects resembles that of stars like the Sun. Our new findings underscore that similarity and imply that some objects comparable to giant planets form the way stars do, from contracting clouds of gas and dust accompanied by disks of their own." These three discoveries together paint a comprehensive picture of planet formation. HOPS 315 shows the starting point, the moment gas condenses into the first solid particles. WISPIT 2b demonstrates the middle stage, a growing planet clearing a gap in its disk. Chapter 1107-7626 reveals that planet formation can be episodic and violent, with dramatic growth spurts punctuating longer periods of steady accumulation. And crucially, planet formation can happen through multiple pathways. Most planets probably form in disks around stars, but some might form independently, like CHAR 1107-7626, more resembling stellar formation than traditional planetary accretion. What does this tell us about our own solar system's formation? Quite a lot, actually. The parallels are striking and instructive. When our solar system was forming 4.6 billion years ago, the young Sun was surrounded by a disk of gas and dust remarkably similar to what we observe around HOPS 315 and WISPIT 2. Temperatures closest to the Sun exceeded 2000 degrees Fahrenheit. At these temperatures, only the most heat-resistant materials could condense into solids: silicon-rich minerals, iron, and nickel. These refractory materials formed first and closest to the Sun, providing the building blocks for Mercury, Venus, Earth, and Mars. Further from the Sun, where temperatures dropped below the freezing point of water, ice could exist as a solid. This is called the frost line or snow line. In our solar system, it was located around 3 to 5 astronomical units from the Sun, roughly where the asteroid belt is today, or slightly beyond, depending on when in the disk's evolution you're measuring. Inside the frost line, rocky materials dominated. Outside the frost line, ice was abundant, dramatically increasing the amount of solid material available for planet building. This explains why the gas giants Jupiter, Saturn, Uranus, and Neptune are so much more massive than the terrestrial planets. They formed beyond the frost line, where there was more raw material to work with. But the story gets more interesting. The frost line wasn't static. As the young Sun's luminosity changed and as the disk evolved, the frost line moved inward and outward. Early in the disk's history, when accretion onto the Sun was vigorous and the disk was heated by viscous dissipation, the frost line sat further out, perhaps as far as 5 astronomical units. As the accretion rate declined and the disk cooled, the frost line migrated inward to perhaps 2.5 astronomical units. This movement had profound implications for planetary composition. Water ice condensing into solid particles beyond the frost line didn't stay put. The ice particles drifted inward due to gas drag, crossing the frost line and sublimating back into vapor.
This created a water vapor trap just inside the frost line, where humidity was high. Dust particles passing through this region could acquire water ice coatings, even though they were technically inside the nominal frost line. This might explain why Earth and the other terrestrial planets contain water, despite forming in the dry inner solar system. They incorporated water-coated dust particles that formed near, but not quite at, the frost line. Jupiter and Saturn likely formed first and fastest among the giant planets. They grew quickly, reaching about 10 to 15 Earth masses within a few million years of the disk's formation. This critical mass threshold is important. Once a planetary core reaches about 10 Earth masses, its gravity becomes strong enough to capture hydrogen and helium gas directly from the surrounding disk. This triggers runaway gas accretion. The planet's mass increases rapidly as it pulls in gas, which increases its gravity, which allows it to pull in even more gas, a positive feedback loop. Jupiter probably accumulated most of its massive hydrogen-helium envelope within just 1 million years, once its core reached the critical mass. It's like a snowball rolling downhill, growing larger as it accumulates more snow, accelerating as it becomes heavier. Saturn formed similarly, but slightly later, or more slowly. It's smaller than Jupiter, suggesting either that it formed further from the Sun, where material was less dense, or that it started forming later and didn't have as much time to accumulate gas before the disk dissipated. The exact sequence and timing remain debated. Some models suggest Jupiter and Saturn formed nearly simultaneously. Others propose Saturn formed tens of millions of years after Jupiter. The discovery of young planets like Wispit 2b helps constrain these models by showing how fast gas giants can form under observed conditions. As Jupiter grew, it began profoundly affecting the rest of the disk. Its gravity stirred up material in nearby regions, increasing collision velocities among planetesimals. At moderate velocities, collisions lead to growth through accretion, but above a threshold velocity, collisions become destructive, shattering planetesimals rather than merging them. Jupiter's gravitational influence pushed collision velocities above this threshold in the region that became the asteroid belt. This prevented a planet from forming there. The asteroids we see today are the leftover planetesimals that never accumulated into a planet, preserved in a chaotic gravitational environment dominated by Jupiter's influence. Jupiter also scattered planetesimals gravitationally. Some were flung inward toward the Sun. Many of these carried water ice even though they formed beyond the frost line. When they impacted the growing terrestrial planets, they delivered their water content. This is thought to be the primary source of Earth's oceans. The water you drink, the water in the oceans, the water vapor in clouds, all of it probably arrived on comets and asteroids scattered inward by Jupiter billions of years ago. We owe our water, and thus our existence, to Jupiter's gravitational influence during the solar system's youth. Other planetesimals were scattered outward into the outer solar system. Some were ejected from the solar system entirely, lost to interstellar space. Others ended up in distant orbits, forming the reservoirs of comets we observe today. The Kuiper belt beyond Neptune and the even more distant Oort cloud contain trillions of icy bodies, remnants from the era of planet formation that got scattered outward and never returned. Occasionally one gets perturbed and falls inward, becoming a comet visible from Earth. Saturn formed slightly later but followed a similar pattern. Uranus and Neptune took even longer, forming further from the Sun where material was more spread out and orbital periods were longer, meaning collisions happened less frequently. They probably didn't finish forming until 100 million years after the solar system's birth, possibly even later. By that time, much of the disk's gas had dissipated, blown away by the Sun's intense radiation and stellar winds during its T-Tauri phase, a violent period all young stars go through. This explains why Uranus and Neptune are smaller than Jupiter and Saturn, despite being called gas giants. They're actually ice giants, with relatively small gas envelopes and large cores of rock and ice. They formed their cores too late to capture massive gas atmospheres before the gas disk disappeared. The terrestrial planets took even longer to reach their final sizes. Earth probably took 50 to 100 million years to reach its current mass. The process involved thousands of collisions between planetesimals and planetary embryos, objects ranging from moon-sized to Mars-sized. These collisions were catastrophic, releasing enough energy to melt entire planetary surfaces. The final stages of Earth's formation were particularly violent. One collision deserves special mention. About 50 million years after the solar system formed, a Mars-sized object that formed elsewhere in the inner solar system had its orbit perturbed, perhaps by Jupiter, and ended up on a collision course with the young Earth. The impact was unimaginably violent. The impactor struck Earth at an oblique angle, excavating an enormous amount of material. Both the impactor and a significant portion of Earth's mantle were vaporized and ejected into orbit. The rest of the impactor merged with Earth's core. The debris orbiting Earth quickly coalesced, forming the Moon within just a few years of the impact. This collision, called the giant impact, is the leading theory for the Moon's origin and explains many of its properties. The Moon's composition matches Earth's mantle. It has a tiny core relative to its size. It's unusually large compared to Earth, unlike most moons of terrestrial planets. All of these features are natural consequences of a giant impact. Can we see similar processes happening around other stars? Yes, that's exactly what HOPS 315, WISPIT2b, and other young stellar systems reveal. The details vary. Different stars have different masses, which affects their temperatures and luminosities. Different disks have different compositions, depending on what materials were available in the gas cloud that formed the star. Different environments, like dense star clusters versus isolated regions, create different conditions. But the fundamental physics remains the same: gravity, condensation, accretion. These universal processes operate everywhere. The observations also address a long-standing question: how common are planetary systems? For most of human history, we didn't know if planets existed around other stars. The first confirmed detection of an exoplanet orbiting a Sun-like star came in 1995, just 30 years ago. Since then, astronomers have discovered more than 5,000 confirmed exoplanets. Thousands more await confirmation. Statistical studies suggest that most stars have planets, perhaps all of them. Planetary systems aren't rare or special. They're the norm.
But here's what we didn't know until recently. How early does planet formation begin? Do planets start forming while the star is still accumulating mass? Or do they wait until the star finishes forming and the disk settles down? The HOPS 315 observations answer this question definitively. Planet formation begins very early. Within the first 100,000 years, the star is barely formed. It's still gathering material from its surrounding envelope, yet solid particles are already condensing. The planetary construction project starts immediately. This has implications for understanding the diversity of planetary systems. If planet formation begins early, while conditions are still turbulent and dynamic, then small differences in initial conditions could lead to vastly different outcomes. One disk might form several gas giants, another might form only rocky planets. A third might form planets that later get ejected, becoming rogues like Char 1107-7626. The timing and sequence of events during these early stages might determine whether you get a solar system like ours, or something completely different. It also affects our search for habitable planets. If we want to find Earth-like worlds, we need to understand how they form. What conditions are necessary? How common are those conditions? The HOPS 315 observations show that the raw materials for rocky planets condense readily in protoplanetary disks. Silicon-rich minerals, iron. These form naturally at the right temperatures, so the ingredients for Earth-like planets are universal. Every Sun-like star probably has them. But ingredients don't guarantee a final product. You need the right sequence of events. The gas giants must form at the right time and the right place. Too close to the star, and they'll prevent rocky planets from forming in the habitable zone. Too far, and they might not protect the inner system from bombardment by comets and asteroids. Jupiter acts as a shield for Earth, deflecting many potentially hazardous objects. Without Jupiter, Earth might have suffered more catastrophic impacts, possibly preventing complex life from evolving. So the architecture of the planetary system matters enormously. WISPIT2b gives us a window into this architecture formation. We're seeing a gas giant in the process of clearing its gap. If WISPIT2b is analogous to Jupiter,
And if other planets are forming in the other gaps, then we're watching a solar system analogue take shape. The inner regions might harbour rocky planets. Wispit 2b occupies the middle region, like Jupiter. Further out, there might be additional gas or ice giants, like Saturn, Uranus and Neptune. The parallel isn't perfect, of course. Every system is unique, but the general pattern matches. The technology enabling these discoveries deserves recognition. The James Webb Space Telescope launched in December 2021. Its 6.5-meter primary mirror and infrared instruments were specifically designed to observe distant, faint objects obscured by dust. Protoplanetary disks are perfect targets. Visible light gets scattered and absorbed by dust particles, but infrared light penetrates through. Webb can peer inside the dusty cocoons surrounding young stars and see what's happening at the heart of planet formation. The Atacama Large Millimeter Array, or ALMA, complements Webb perfectly. Located 16,500 feet above sea level in Chile's Atacama Desert, ALMA consists of 66 radio dishes working together. They observe at millimeter and submillimeter wavelengths, even longer than infrared. At these wavelengths, ALMA can map the distribution of molecules throughout protoplanetary disks. It can measure velocities, temperatures, and densities. It can trace how material flows through the disk, where it accumulates and where it's being depleted. Combined, Webb and ALMA provide unprecedented insight. Webb sees the hot inner regions where minerals condense. ALMA maps the cooler outer regions where ice forms. Webb detects molecules through their infrared emission. ALMA detects them through their radio emission. Together, they create a complete picture from the inside out. Ground-based telescopes with adaptive optics, like the Magellan and Very Large Telescopes, add another crucial capability. They can take high-contrast images that suppress the star's glare and reveal planets nearby. This is extraordinarily difficult. A Jupiter-mass planet is roughly 1,000,000 times fainter than its parent star. Detecting such a faint object next to such a bright one is like trying to see a firefly hovering next to a searchlight. Adaptive optics systems correct for atmospheric blurring in real time, sharpening images to near theoretical limits. Coronagraphs block the star's light, creating an artificial eclipse. These techniques combined enabled the detection of Wispit 2b and similar planets. Future missions will push these capabilities even further. The European Extremely Large Telescope, currently under construction in Chile, will have a 39-meter primary mirror. That's 6 times larger than Webb. It will be able to image smaller, fainter planets and study their atmospheres in detail. NASA's Nancy Grace Roman Space Telescope, launching in 2027, will survey enormous regions of sky, finding thousands of planets through gravitational lensing techniques. These missions will transform our understanding of how common Earth-like planets are and whether they typically have the conditions necessary for life. The discoveries also raise profound philosophical questions. If planets form everywhere, around nearly every star, then the galaxy contains hundreds of billions of worlds. Some are scorching hot, orbiting close to their stars with surface temperatures exceeding 1,000 degrees Fahrenheit. Others are frozen wastelands, drifting in the outer darkness where sunlight barely reaches and temperatures hover just a few degrees above absolute zero. Some are massive gas giants like Jupiter with no solid surface to stand on, just endless layers of hydrogen and helium compressing down to exotic metallic states in their cores. Others are small and rocky, with surfaces of stone and metal. A fraction of them might be Earth-like, temperate worlds orbiting in their star's habitable zone, that special distance where temperatures allow liquid water to exist on the surface, not too hot that water boils away, not too cold that it freezes solid, just right for liquid oceans, and where there's liquid water, there might be life. At least, that's what we know from Earth. Life as we understand it requires liquid water as a solvent. All terrestrial biochemistry uses water. Every living cell on Earth is mostly water. It's plausible, perhaps even likely, that life elsewhere would also require water. Though we can't rule out exotic biochemistries using different solvents like liquid methane or ammonia, water seems like the best bet based on its unique chemical properties. How many such worlds exist? This question motivates an enormous amount of modern astronomy and planetary science. The answer depends on several factors, each uncertain to varying degrees. First, what fraction of stars have planetary systems? We now know the answer is high, probably close to 100%. Nearly every star has planets. Second, what fraction of those systems have planets in the habitable zone? This varies by star type. Sun-like stars have habitable zones around 0.95 to 1.4 astronomical units. M-dwarfs, the most common star type, have habitable zones much closer, around 0.1 to 0.2 astronomical units, because they're dimmer than the Sun. Observations suggest at least 20% of Sun-like stars have a planet in their habitable zone. For M-dwarfs, it might be 40% or higher. Third, what fraction of planets in the habitable zone are actually Earth-like? Having the right distance from the star isn't enough. The planet needs to be the right size. Too small, and it can't hold an atmosphere. Mars is an example. It's in the Sun's habitable zone, or at least its outer edge, but it's too small. Its weak gravity couldn't retain a thick atmosphere. Any water on its surface eventually evaporated and was lost to space. Too large, and a planet might become a mini Neptune with a thick hydrogen-helium envelope obscuring any rocky surface beneath. The sweet spot seems to be roughly 0.5 to 2 Earth masses. Not too big, not too small. Fourth, the planet needs to actually have water. Being in the habitable zone doesn't guarantee water is present. The planet needs to have incorporated water during formation or received it afterward through comet and asteroid impacts. This depends on the disk composition and delivery mechanisms. Observations of protoplanetary disks, like HOPS 315, reveal that water is common in the outer disk regions beyond the frost line. But getting that water to planets forming in the habitable zone requires some transport mechanism. Giant impacts, like the ones that shaped our solar system, can scatter water-rich material inward. So can gravitational perturbations from migrating giant planets. Fifth, the planet needs a stable climate over billions of years. This requires several things. A stable orbit, which means no close encounters with other planets or massive gravitational perturbations. A magnetic field to shield the atmosphere from the star's stellar wind, which would otherwise gradually strip away the atmosphere, like Mars lost most of its atmosphere. Plate tectonics or some equivalent mechanism to regulate atmospheric carbon dioxide and maintain climate stability through the carbonate-silicate cycle. Earth has been habitable for billions of years, largely because plate tectonics recycles carbon between the atmosphere, oceans and rocks, preventing runaway greenhouse or icehouse conditions.
Apply all these filters and what do you get? Conservative estimates suggest perhaps 1% to 5% of Sun-like stars have a truly Earth-like planet. That might sound low, but the Milky Way contains about 100 billion stars, of which roughly 10 billion are Sun-like. 5% of 10 billion is 500 million Earth-like planets in our galaxy alone. And there are hundreds of billions of galaxies in the observable universe. The numbers become almost meaningless at this scale. Even if Earth-like planets are relatively rare by percentage, the sheer number of stars ensures that billions or trillions of them must exist. This brings us to perhaps the most profound question of all. If Earth-like planets are common, is life common? We have a sample size of 1, life on Earth. We don't know how hard or easy it is for life to emerge from non-living chemistry. If it's easy, happening readily wherever conditions are right, then life might be everywhere in the universe. Billions of inhabited worlds, potentially millions of technological civilizations. The galaxy could be teeming with life, from microbes to intelligence. On the other hand, if abiogenesis, the origin of life from non-life, is extremely difficult, requiring such a specific and unlikely sequence of chemical events that it happens only once per galaxy or less, then we might be alone, or nearly so.
We don't know which scenario is correct. The Fermi paradox captures this uncertainty. If intelligent life is common, where is everybody? Why haven't we detected radio signals from alien civilizations? Why haven't we found evidence of their presence? Maybe they don't exist. Maybe intelligence is much rarer than simple life. Maybe technological civilizations destroy themselves before they can spread across the galaxy. Maybe they're out there, but using communication methods we haven't imagined yet. Maybe they exist, but don't feel compelled to advertise their presence. The paradox remains unresolved. But here's what we can do. We can search. The James Webb Space Telescope isn't just observing planet formation. It's also characterizing the atmospheres of mature exoplanets. By observing a planet's spectrum as it transits in front of its star, Webb can identify molecules in the planet's atmosphere: water vapor, carbon dioxide, methane, oxygen. Some of these molecules could be biosignatures, signs of life. Oxygen, for example, is highly reactive. It shouldn't persist in a planet's atmosphere unless something is continuously producing it. On Earth, that something is photosynthetic organisms, trees, algae, cyanobacteria. They've been pumping oxygen into our atmosphere for billions of years, maintaining concentrations around 21%. If we detected similar oxygen levels on an exoplanet, it would be strong evidence for biology. Other biosignatures include atmospheric combinations that are out of chemical equilibrium. Oxygen and methane, for example, react with each other and shouldn't coexist at high concentrations without continuous replenishment from biological or geological sources. Detecting both in an exoplanet's atmosphere would raise questions. What's producing them? Volcanoes can produce methane, but volcanoes don't produce oxygen. Life produces both. Not definitive proof, but compelling evidence. Phosphine in atmospheres might be another biosignature. On Earth, phosphine is produced only by anaerobic bacteria or industrial processes. It's toxic to oxygen-breathing life and very short-lived in the atmosphere. If we detected phosphine on an exoplanet, it would suggest biological production, though we'd need to rule out exotic abiotic chemistry first. The discovery of phosphine in Venus's atmosphere in 2020, later disputed and still controversial, shows how careful we must be with biosignature claims. Extraordinary claims require extraordinary evidence. Within the next decade, Webb and other telescopes will observe dozens of potentially habitable exoplanets. We'll characterize their atmospheres. We'll search for biosignatures. If life is common, we might find evidence for it soon. Within our lifetimes, we could answer one of humanity's oldest questions. Are we alone? The observations of HOPS 315, WISPIT-2b, and similar young systems inform this search. They tell us how planets form, how common Earth-like worlds are, and what conditions prevailed during their formation. This knowledge narrows the search space and tells us where to look. The young stellar systems also teach us about cosmic timescales and our place in time. HOPS 315 is 100,000 years old. To us, that sounds ancient. 100,000 years ago, anatomically modern humans were just beginning to spread from Africa to other continents. We were hunter-gatherers living in small bands with no agriculture, no cities, no writing. The entire span of recorded human history, all of civilization, spans only about 5,000 years. That's 5% of HOPS 315's current age. Yet in cosmic terms, HOPS 315 is brand new, an infant. It has tens of billions of years ahead of it, possibly 100 billion or more, depending on its exact mass. The planets forming around HOPS 315 right now, those silicon-rich minerals condensing from gas into solid grains, will exist for longer than Earth has already existed. Earth is 4.6 billion years old. The Sun will last another 5 billion years before exhausting its hydrogen fuel and swelling into a red giant that engulfs the inner planets. So Earth has roughly half its lifetime remaining. But a planet forming around HOPS 315 today has its entire lifetime ahead of it. 10 billion years of orbital evolution, of geological changes, of potential biological development if life arises there. These worlds we're watching being born will still be orbiting their star long after our Sun has died. they'll outlast us by eons. This perspective is simultaneously humbling and awe-inspiring. Individual human lives span decades. We get perhaps 80 or 100 years if we're fortunate. Civilizations span millennia. Ancient Egypt lasted roughly 3,000 years. Rome, about 1,000. Modern nations rarely exceed a few centuries before transforming into something different. Species last millions of years. Homo sapiens has existed for about 300,000 years. We might persist for another few million before evolving into something different or going extinct. Even the Earth will eventually be destroyed when the Sun dies. But the universe? The universe operates on timescales billions or trillions of times longer than any of these human scales. Stars live for billions to trillions of years depending on their mass. Small red dwarfs can last 10 trillion years, slowly fusing their hydrogen until none remains, then cooling over eons into dim stellar embers. Galaxies persist for hundreds of billions of years, their stars recycling gas through generations of stellar birth and death, slowly consuming their available fuel, but taking so long that the galaxy outlasts all but the most long-lived stars. The universe itself is 13.8 billion years old. It will continue expanding for trillions upon trillions of years. Eventually, all stars will die. All matter will decay or fall into black holes. Even black holes will evaporate through Hawking radiation, taking inconceivable spans of time measured in 10 to the power of 100 years or more. The universe will end in a cold, dark, empty state, all structure and energy dissipated into a thin soup of photons and exotic particles. But that's so far in the future that the numbers lose all meaning to human comprehension. We are infinitesimally small temporal blips in an almost infinite cosmos. We exist for an eye blink in cosmic time. Yet we've developed the ability to understand that cosmos, to measure it, to trace its history backward 13.8 billion years to the Big Bang, to predict its future trillions of years forward to heat death, to understand how stars form from collapsing gas clouds, how planets condense from protoplanetary disks, how life emerges and evolves, how intelligence arises and develops technology, how consciousness becomes aware of its own existence and its place in the vast universe. Small as we are, brief as our existence is, we can comprehend the vastness of space and time that surrounds us. That is extraordinary. That is what makes us special, if anything does, not our size or longevity, but our capacity for understanding. These questions motivate much of modern astronomy. The search for biosignatures, molecules in planetary atmospheres that could indicate biological activity, oxygen, methane, phosphine. If we can characterize the atmospheres of Earth-like exoplanets, we might find chemical imbalances that require life to maintain them. That would be the discovery of the millennium, proof that life exists beyond Earth, even if it's just microbial, even if it's billions of light years away. Just knowing we're not alone would fundamentally alter humanity's perspective on our place in the cosmos. But before we can search for life, we need to understand planet formation. We need to know how often Earth-like worlds form. What fraction orbit in their star's habitable zone? How often do they have the right ingredients? Water, organic molecules, a protective atmosphere, a magnetic field to shield against radiation, stable conditions for billions of years. Each requirement filters out some fraction of planets. By the time you apply all the filters, how many Earth-like worlds remain? The answer depends critically on understanding the formation process. That's why HOPS 315, WISPIT2b, and CHA 1107-7626 matter so much. They're not just individual discoveries, they're pieces of a larger puzzle. Each observation adds detail to our understanding of how planets form, how common different types of planets are, and what conditions lead to Earth-like worlds. The more we learn, the better we can estimate how many potentially habitable planets exist in the galaxy, and the better we can target our searches for biosignatures and signs of intelligence.
The rate at which we're making discoveries is accelerating. 30 years ago, we had no confirmed exoplanets. 10 years ago, we had a few hundred. Now, we have thousands. The pace keeps increasing as instruments improve and techniques become more sophisticated. Within another decade, we might have characterized hundreds of Earth-like atmospheres. Within a generation, we might have detected biosignatures. The answer to whether we're alone could come sooner than most people realize. These young stellar systems also teach us about cosmic timescales. HOPS 315 is 100,000 years old. To us, that sounds ancient. 100,000 years ago, anatomically modern humans were just beginning to spread out of Africa. Written history spans only about 5,000 years. Recorded astronomy, perhaps 3,000 years. The entire span of human technological civilization could fit into the last second of a day that represents HOPS 315's lifetime. Yet in cosmic terms, HOPS 315 is brand new, an infant. It has tens of billions of years ahead of it. The planets forming around it now will exist for longer than Earth has already existed. These worlds we're watching being born will still be orbiting their star when our sun has exhausted its fuel and died. This perspective is both humbling and awe-inspiring. We are fleeting. Individual human lives span decades. Civilizations span millennia. Species span millions of years. But the universe operates on scales billions of times longer. Stars live for billions of years. Galaxies for hundreds of billions. The universe itself is 13.8 billion years old and will continue for trillions more. We are infinitesimally small temporal blips in an almost infinite cosmos. Yet we've developed the ability to understand that cosmos, to measure it, to trace its history, to predict its future. Small as we are, we can comprehend the vastness. That comprehension comes from observations like these: patient, careful measurements of distant stars, painstaking analysis of spectral lines and image pixels, theoretical models that explain what we're seeing. The scientific method in action: hypothesis, prediction, observation, revision. Slowly, incrementally, our understanding improves. Mistakes get corrected, gaps get filled. The picture becomes clearer. 50 years ago, we didn't know if other stars had planets. Now we know they do. We didn't know how planets formed. Now we're watching it happen. We didn't know if Earth was unusual. Now we're finding planets everywhere, some similar to Earth, some wildly different. Each answer raises new questions. That's how science works. Understanding creates new puzzles. But the direction is always forward, toward greater knowledge, deeper comprehension. The astronomers who made these discoveries dedicated their careers to this work. Years of training, decades of experience, countless hours writing proposals, analysing data, troubleshooting instruments. The observations themselves might take only hours or days, but the preparation takes years. The analysis takes months. The interpretation requires deep knowledge of physics, chemistry, and planetary science. This is specialised work performed by experts at the peak of their fields.
Yet the results belong to all of us. Scientific knowledge is public. Papers get published in open journals. Data goes into archives available to anyone. The discoveries become part of humanity's collective understanding. When students learn about planet formation in school, HOPS 315 will be in their textbooks. When tourists visit planetariums, they'll see images of Wispit 2b's disk. The knowledge spreads. It becomes foundational. It shapes how future generations think about the universe and our place in it. This is the power of astronomy. It doesn't just satisfy curiosity, though it certainly does that. It doesn't just enable practical applications, though space technology has countless uses. Astronomy expands our perspective. It reminds us that Earth is one world among countless others, that our Sun is one star in hundreds of billions, that our galaxy is one of trillions, that we inhabit a universe vast beyond imagining, yet comprehensible through observation and reason. The baby planets forming around HOPS 315 and WISPIT 2 won't be visited by humans. They're far too distant. Light takes 1,300 years to travel from there to here. The fastest spacecraft we've ever built would take tens of millions of years to reach them. These worlds will never be more than points of light in our telescopes. We'll never walk on their surfaces, breathe their air, or see their sunsets with our own eyes. They will remain forever distant, accessible only through the photons that cross the vast emptiness of space to reach our instruments. Yet we can study them, we can understand them, we can measure their properties, deduce their compositions, predict their futures. Through science, the inaccessible becomes knowable, the unreachable becomes understood. We may never physically touch these distant worlds, but we can know them as well as we know the planets in our own solar system, perhaps better, since we're observing them at a stage our own planets passed through billions of years ago. We're seeing our past written in their present. That's the beauty of astronomy. It's time travel. When we observe HOPS 315, we see our solar system as it was 4.6 billion years ago. When we study WISPIT 2b clearing its gap, we witness Jupiter's formation. When we watch CHAR 1107-7626 growing episodically, we might be seeing processes that affected all planets, including Earth, during their violent youth. The past isn't gone, it's still happening elsewhere, if we know where to look. The discoveries will continue. Every year brings better instruments, more sensitive detectors, cleverer techniques. The James Webb Space Telescope is just beginning its mission. It will operate for at least another decade, probably longer. ALMA continues surveying the skies. New telescopes are under construction. The flood of data will only increase. Within our lifetimes, we'll map thousands of protoplanetary disks, image hundreds of forming planets, watch dozens of stellar systems evolve from infancy to maturity. The story of planet formation will go from hypothesis to observed fact, from theoretical prediction to documented process. And each new observation will refine our understanding. We'll learn which factors determine whether a planetary system resembles ours or develops differently. We'll discover what fraction of systems form habitable worlds. We'll find out how common the ingredients for life are, and how often those ingredients actually lead to biology. The questions that have puzzled humanity for millennia. Are we alone? How did we come to be? What is our place in the cosmos? These ancient questions will finally have scientific answers grounded in observation. We live in a golden age of astronomy. Never before have we had such powerful tools to explore the universe. Never before have so many mysteries been within reach of solution. The baby planets forming around young stars aren't just scientific curiosities. They're our origin story. They're the key to understanding how common or rare Earth-like worlds might be. They're windows into processes that created everything we know, including ourselves. The silicon-rich minerals condensing around HOPS 315 are made of the same atoms as the rocks beneath our feet. The water ice forming beyond the frost line in distant disks is chemically identical to the oceans covering Earth. The organic molecules detected in protoplanetary disks include the same carbon-based compounds that make up our bodies. We are made of stardust. Not metaphorically, but literally. Every atom in your body was forged in stars, scattered by supernovae, and incorporated into the disk that formed our solar system. The same atoms cycling through stellar birth, planetary formation, and biological evolution. From stars, to planets, to life, to consciousness. An unbroken chain of cosmic evolution billions of years long. Understanding planet formation isn't just about distant worlds. It's about understanding ourselves. Where we came from, how we came to be, why Earth has the properties it does, why life emerged here. The story written in the rings and gaps of protoplanetary disks is our story. The baby planets being born around young stars today are our cosmic siblings, separated by space and time, but sharing a common origin, in the universal processes that build worlds. Thank you so much for joining me on this journey through the cosmic nurseries where planets are born. We've witnessed the earliest moments of world formation, seen planets clearing gaps in their disks, and watched rogue worlds experiencing dramatic growth spurts. These discoveries represent some of the most exciting developments in astronomy this year, revealing the processes that created our own solar system billions of years ago. If you enjoyed learning about these baby planets and want to hear more about the latest astronomical discoveries and cosmic mysteries, please subscribe to stay updated. Until next time, keep looking up at the stars and wondering about the countless worlds being born among them. Clear skies.